Welcome to experiment number 1, and for this experiment, we are going to introduce circuit modeling using OrCAD PSpice. The objective of this experiment is to familiarize with the PSpice simulation software, to capture diagram of switching circuit, and to model the switch based on the set parameters. For the part 1 of our experiment, we are going to make a voltage-controlled switch in PSpice. To start our project, let's go to File, New, then click Project, then let's name this experiment 1, OK. Create blank project, then OK. Here in our circuit design, we have a pulse voltage source that is connected to the S brake switch. We have a 2 ohm resistor and a DC voltage source of 24 volts. So in the OrCAD PSpice, let's go to Place, and PSpice component, then let's search. Then let's type vpulse. So here, pulse voltage source, double click. There. Then let's maximize. Then let's search for S brake. Double click there. Then for the resistor, go to Place, PSpice component, resistor, rotate, go to Place again, PSpice component, source, voltage sources, DC, there. Then let's connect the components, place wire, there. For the ground, let's click here, place ground, 0 cap seam, OK, place ground here and place ground there. Let's modify the value of the resistor, 2 ohms. The value of the DC voltage source to 24 VDC. 24 VDC. Let's name the vpulse as our control voltage, V control. For the parameters of our control voltage, V1 will be set to 0. V2 will be set to 5 volts. TD or time delay will be 0. The rise time is 1 nanosecond. Fall time is also 1 nanosecond. For the pulse width, its value is 10 microseconds. For our period, it will be 25 microseconds. So as you can see, our control voltage source has a rise time and fall time that are made small in value compared to our pulse width and period. The V1 and V2, which is the on and off voltage levels for the switch, is 0 and 5 volts. For the S brake, we will also modify its value. So let's click S brake, then edit. Then edit PSpice model here. So PSpice AD, OK. For our PSpice model editor, we will only modify the R on value to 0.001 ohms. So let's modify 0.001. Then let's click Save X. To simulate our circuit, let's go to New Simulation Profile here. Then let's name this experiment 1, create, then PSpice AD, OK. So for our simulation settings, our analysis type is time domain transient. For our runtime, we will set it to 80 microseconds. Apply, and OK. Then let's simulate here, run PSpice, the play button. In the simulation, we will test the switch control voltage and the load resistor voltage. First, let's go to trace, add trace. Then let's type in the trace expression V, in close parentheses, V control positive. Then click OK. In the simulation, the switch control voltage, wherein the peak voltage of the pulse waveform is 5 volts. To recall, we set our control voltage to have a pulse width of 10 microseconds in a period of 25 microseconds. As you can see here, the pulse width in 5 volts lasted for 10 microseconds. Then it rises again after 25 microseconds, meaning in a cycle of 25 microseconds, there is a pulse that will last for 10 microseconds. Now to test our load resistor voltage, let's click here. Then let's modify the trace expression to VR1, which is the name of our load resistor. Then the value of the resistor, 2, in close parentheses, OK. For our load resistor voltage, we recorded a peak pulse voltage of 24 volts that lasts for 10 microseconds. Then it rises again after 25 microseconds. In comparison with the switch control voltage, the waveform that we see here in our load resistor voltage is in phase with the switch control voltage. It is because it has an identical rise time and fall time as the switch control voltage waveform. The only difference between each other is the peak voltage of the pulses. For part 2 in experiment number 1, we will use a transistor as switch. For the circuit design, we will be modifying the previous circuit, wherein our switch will be IRF 150 MOSFET instead of a S brake. We will also place a 10 ohm resistor here and label it as RG. Now let's go to OrCAD. Let's delete it. Now let's go to Place, PSpice component, search. Let's search IRF 150. So let's click IRF 150 MOSFET. There. Then let's copy a resistor here. For our RG, state RG, and let's rename this as our load. Okay, let's set our RG to 10 ohms. Okay, let's also remove the ground here in our control voltage. Then let's connect our circuit. So let's place a wire. For the parameters of our control voltage, it will have the same rise time and fall time, which is 1 nanosecond, with a pulse width of 10 microseconds, with a period of 25 microseconds. For our V2, we will change the 5 volts to 12 volts. Then, for our simulation profile, analysis type, time domain transient, and our runtime time is 80 microseconds. Apply. Okay. Run PSpice. So in the part 2, we will also test our switch control voltage and load resistor voltage. Let's go to trace, add trace, then V control, positive, and close parentheses. There. In the simulation of part 2, we can already tell the difference between the previous circuit design using S-break as our switch and using transistor MOSFET as our switch. Now let's measure the peak voltage value in our switch control voltage. Let's click here, cursor on, then here. So in our cursor, we recorded a value of 35.683 volts. We can also see the rise time and fall time. Here, look. In the previous simulation, we can hardly see the rise time and fall time of the pulse waveform. But here, we can somehow see that our pulses follow the parameters of our control voltage, wherein it has a fall time of 1 nanosecond and a rise time of 1 nanosecond here. You can see the slight slant of our pulse waveform. And it also follows the control voltage parameters, wherein the pulses last for 10 microseconds, then falls for 1 nanosecond, then 0 voltage, and rises again for 1 nanosecond, and peaks again for 10 microseconds. Now, let's test the load resistor voltage. Let's go here, then modify the trace expression. V, our load, 2. Okay, now let's test the peak voltage value of our pulse in our load resistor voltage simulation. Now let's go to cursor, let's move here. We recorded a peak voltage value of 23.683 volts. So you can see it also rises for 10 nanoseconds, then the peak voltage lasts also for 10 microseconds and falls for 1 nanosecond, then 0 volts for 15 microseconds. From there, it completes a 1 cycle with a time of 25 microseconds. From this experiment, we can conclude that we can use different types of designs for our switches. In part 1, we use S-break for a switch, wherein the source control voltage is lower than the resistor voltage. And using MOSFET transistor as our switch, it resulted to a load resistor voltage lower than the switch control voltage.